Hey everyone, welcome to the second video for section 3.8. So in this video we're going to get into actually solving the equations for the forced and damped oscillator and seeing what kind of stuff we can get out of that and what kind of sort of weird behaviors can happen depending on the frequency of your forcing compared to the natural frequency of your system. So let's go ahead and take a look at that. So for this video and probably for the next couple as well, we're going to assume that our forcing function is oscillatory. So assume that f of t is some f0, or f0 is some constant, cosine of omega t, omega is some frequency. And we're looking to solve mu double prime plus gamma u prime plus ku equals f0 cosine of omega t. Now, in general here, we're going to assume we're in the underdamped case, which means we're going to get sines and cosines on the left-hand side, but it doesn't really matter. It all works out the same way at the end. So we know we have a transient solution from our solution to the homogeneous problem. So our transient solutions is C1 U1 of t plus C2 U2 of t, and this goes to 0 as time goes to infinity based on the fact that it's a transient solution. We are basically just going to ignore that and just focus on the forced response. So how can we solve for the forced response here? Well, the right-hand side has a cosine of omega t term, which means if I've wanted to use a method of undetermined coefficients to solve for my capital U, I'll want that U of t equals a cosine of omega t plus b sine of omega t. Plug that all in for U, take derivatives, multiply by the constant, solve it out, and see what you get. Now, I'm not going to do all that work here. That is a method for undetermined coefficients. It's not difficult, it's just a lot of algebra to figure that out. But then we can do is we can convert this into something of the form r times cosine of omega t minus delta, just like we did in section 3.7 for the unforced cases. We can convert our a cosine omega t plus b sine omega t into a r cosine omega t plus delta, which also talk about the amplitude, the phase factor, and the frequency of this oscillation. Now, again, I'm not going to do all the work for this as well, but I'll write the formulas. We can sort of talk about them a little bit. So if you do all the work, you write out A and B, you find them, you solve for R, you plug things in, you get something that looks like this. You get that R, so these are formulas. R is going to be F0, the amount I'm forcing it by, divided by delta. I'll write delta later. The tangent of little delta is gamma times omega over m times omega 0 squared minus omega squared. Omega 0 here, omega 0 squared is k over m. This is the natural frequency of the unforced system. And then this delta term is the square root of m squared omega 0 squared minus omega squared plus gamma squared omega squared. So those are kind of nasty formulas, but you will know omega 0 because that's from the natural frequency of the system. You will be given omega because that's the right-hand side, and then your m and your gamma are parameters of the problem. So these are the formulas you get for all of these terms, and they're just sort of there. Now there's something sort of interesting that can happen here, and it involves this delta term and the amplitude r. You would originally initially assume that, so say I only force this with magnitude 1 force up and down. Well, you would assume that I couldn't go much further than, say, like 1 over k, because 1 over k would then tell me the amount the string would stretch if I just pull it with a constant force of 1 Newton. Right? That's the equilibrium length is just the force divided by the spring constant. So if I pull it with 1 Newton, it should go a certain distance and stay there. Now, the thought is if I'm oscillating back and forth with the same force, it shouldn't be able to go any further than that. However, that's not necessarily the case. Let's take a look at what r ends up being compared to this ratio f naught over k, because f naught over k would be the force if I didn't oscillate and just pulled it directly, and r is the amplitude of the oscillation when I do oscillate. So let's see what that looks like. So I'm going to look at the ratio of f0 divided by k to r. And now just by looking at what I have for my setup, this is delta over k. And I'm not going to do all the messy algebra. It involves pulling out a w naught squared from the entire inside of the square root sign, simplifying things out, canceling things. And what you end up seeing is this turns into this expression, this nasty thing here. Now, and we see again over on the right here, this capital gamma, this ratio gamma squared over km that I mentioned in one of the earlier videos, that was going to come back and going to be important. And this is why. So if you look at this expression, what happens if gamma is tiny and omega is pretty close to omega 0? Well, then this first term is going to be small. This second term is going to be really small, which means the ratio is going to be really tiny, which means that r in this case is going to be much, much larger than f0 over k. Because if f0 over k divided by r is really tiny, then r has to be huge compared to f0 over k, which means the amplitude of my oscillation is going to be big compared to what it would be if I just pulled on the spring with that certain force. And this idea is called resonance. This is the fact that because I'm oscillating at a frequency that's close to the natural frequency of the system, I get benefits out of that. That means my oscillation becomes bigger and gets stronger because of the fact that I have this resonance system, that I'm oscillating close to the natural frequency and there isn't too much damping. So in order to make the point about this, I'm going to show you some pictures drawn by Maple as to what happens as you change the different coefficients and see what you get. All right, so let's go ahead and look at this here. So this graph doesn't really too make sense, but I'll start moving things around in a second. So I've set up code here to draw what this sort of graph looks like for different values of omega, which is just W here, which is my forcing frequency. I have set K to be 1 just because I picked a number for it. Right now damping is 0. We'll change that a little bit. We'll make that say 0.5. And this gives me the gamma value, which is damping squared over mk. M is just 1 here. It gives me omega 0, which is the natural frequency of the system. It gives me what this ratio looks like. And then it solves the ODE with the proper setup, solves it starting at 0, 0, and just shows you what happens over time. So let's just run this and see what happens. So let's just run this and see what happens. So we run this with a forcing frequency of 0.5. We see that our natural frequency here is 1. So we're a decent amount below. We're at 0.5 versus being at 1. So the ratio there is going to be 2, or 1/2. And then you run things out and you get something fairly smooth. You get sort of an oscillation here. Although you'll see the oscillation has a magnitude bigger than 1. Right? It's an oscillation of somewhere around like 1.3 up and down here, which is more than the 1 force you put into it. So here we're getting a little bit of resonance. If I get a lot closer to 1, say I put in 0.99, then the resonance is even bigger. Now we're up to a whole height of 2 at each of these peaks. And again, you see this sort of transient solution at the beginning here, right? It starts a little small, it starts lower, but it builds up over time because after a while, this transient solution, which is going to compete against it, starts dying off. And I just get my standard oscillation once I get up to here at the end. Now, if I make the frequency huge, say I make it like 5, we're not getting resonance anymore. Right, we're forcing this thing so fast in a circle that it doesn't even really go very far at all. And our oscillation ends up capping out at around like 0.04. So when we were near resonance, near the same frequency, we had a height of like 2 or 3. But if we're farther away, we're more in the range of a height of like 0.04. So this resonance really affects how the solution vibrates and what you actually get out of the answer when you start vibrating this back and forth. So that's what can happen when you have a forced damped oscillator and you force it with a periodic force. You can either get some things that cancel out and you get almost nothing out of it if you're vibrating too fast, or if you are really close to resonance, you get really, really big waves. You get waves at a height twice as big as the ones from before. And if I make my damping coefficient even smaller, I can get things that are even bigger than that. I can get things that are huge because the smaller my damping coefficient gets, the smaller this gamma constant gets, which means the more my R is bigger than my F0 over K. All right, so that was the point of this video, to get those points across to you about the resonance that happens in the damped case. This is more what you would call physical resonance, because in this case, if there is damping, there's damping in pretty much every system you have because there's air resistance. So this kind of resonance happens a lot and can actually happen with things in the world that you're trying to model. The stuff we'll talk about in the next video, which is undamped resonance, is a little less physical because undamped really doesn't happen ever. But if it's close, you can get something that's similar that works out in the end. So that's it for this video. The next one we'll talk about the undamped oscillator that's forced and see what kind of happens there and how resonance shows itself in that case as well. Thanks a lot for watching, and I'll see you in the next one.